from the article I gave you, or from the article we read, from the history of science, when people studied motion, they try to separate motion into two different types. The first one is natural motion, which doesn't need any reason. Okay, the reason is happen naturally, so no reason, okay, or no need for any explanation. And on the other hand, there is a violent motion, which we need some explanation. Which we need explanation. Okay, and from our concept now, or from the ideas, we know now this explanation is false. Okay, so let's back to the history. From Aristotle, he proposed the reason for the flying arrow is there is a motive force to keep things move. Motive force to keep it move. So, and the air is squeezed here, so here become a vacuum, and because air doesn't like a vacuum, so the air rush into, fill the vacuum, okay, and then create a force to make an arrow flying forward. Okay, so this is the idea of like Aristotle gave to this explanation. Okay, so this is from BC 350. About 800 years later, John Philoponus, he proposed another idea, which he named impressed force. Okay, and the impressed force is from the ball and transferred to the arrow. Okay, but the important thing is the reason why the arrow is going to slow down is because the impressed force will gradually die out. So the impressed force will gradually die out. Gradually. And then another 1,000 years later, Jean Bourdin, he proposed the impressed force. He changed the idea or the name of impressed force to impetus. Okay, different from impressed force, is from ball as well. Okay, but the ball, after he transfer the impetus to the arrow, and the arrow will stay. This is the internal state. Okay, and this is depending on the arrow's weight and the speed. The arrow's weight and speed. Okay, so this won't change. Okay, they have the same amount of impetus from the beginning to the end. So different from impressed force, the impetus won't die out. Okay, and the reason that the arrow was slowing down, okay, or stop, is because of air friction or air resistance. Okay, so he is the first person try to create the motion can be depending on the internal property or internal state. And then another, now it's 300 years later, 400 years later, Galileo start to name or propose another concept called inertia. And inertia, the main idea is when there's no external influence, say for example air friction, so no external influence or no external, say, force. Okay, and they will keep moving. Okay, Galileo think it will keep in the line, infinite horizontal plane. Okay, but soon this one will become like, I think from the article we learned, okay, they will move infinitely. So actually in Galileo's idea, inertia is moving in a circular motion. Okay, but actually this is wrong. Okay, so Descartes, he changed this idea into like you know, he applied to all the objects, okay, and then he knows this one is moving to a straight line, okay, and we learn the idea when there's a rotating stone, and if we cut the string and they will move in a tangent direction is from him, okay, from Descartes, okay. And this person, Pierre Gassendi, his idea is modified from Galileo's inertia, okay, Descartes' inertia, to the very close to our current understanding about Newton's first law of motion, okay, which is, okay, when there's no external force and the object is moving in constant velocity, constant speed, and in a straight line, and in a straight line, in a straight line. Okay, and you know, because the velocity is a vector, so when the speed is not changed, that means the speed won't change and the direction won't change, so it is a straight line. And now, in the second law, okay, based on this understanding or the concept of inertia, so when we have an external force, and it will cause what? It will cause acceleration, change of speed, which is acceleration. And you know, from year 11 and year 12, you know acceleration is the change of velocity over time. So the external force is going to cause acceleration, and it is inverse proportional. Acceleration is inverse proportional to the mass. So when we got more mass, okay, when the mass is bigger, and A will be smaller, and in other words, they are inverse proportional. They are inverse proportional. Okay, they are inverse proportional. An important concept from here you need to know is when we talk about inertia, and actually mass is the inertia. Mass is the quantitative measure of inertia. So when the mass is bigger, inertia is bigger, so it's more difficult to change the speed. Okay, so that's the less acceleration. Okay, and based on this understanding, we need to talk about mass and weight. Okay, I think you know already from year 11 and year 12. Okay, weight is a force. Okay, so if this is Earth, and we have an object here, like a mass here, okay, and if we release it, and it will drop total to Earth with the acceleration for how much? For 9.8 meter per second. Okay, so which will be what? If we apply F equals ma, Newton's second law, and you know F equals ma, okay, and m is the mass, and you times 9.8, and that becomes, say, Newton. Okay, and this is actually the idea of weight, and the unit is Newton. Okay, and then for Newton's third law, it's action and the reaction. Am I right? It's action and the reaction. So when there's action and reaction, okay, so when there's a pair, so there's an object, and if someone push the object, and the object will push the person back. Okay, so it's action and reaction pair, which will link to momentum conservation, and we'll talk about this one later. Momentum conservation. Okay.